too late. It's not a race, huh?
Yeah, I was worried because I had to send him a message. Okay, everybody. So before we go forward to the last class from Pasquale Serpico, we have a few treats for you. One of your colleagues, Ernesto, left some chocolates that were going to be served in the next coffee break. Pasquale Serpico is donating few tickets that will be for the metro that will be assigned to the first 3 questions after his class, and the other 3 are going to stay there. And this is the list for the social dinner, which is going to take place next Wednesday. Okay? If you plan to attend, the director is paying for it. So please put yes, so I have a count by tonight, and I can tell him the amount of persons. You can come, just put a yes after the class. Okay?
Okay, so I should switch this one on. Yes, it's working, I hope. Yes, it's on. It's on. Okay. Good morning. The good news is that you are going to get rid of me very soon. Final lecture. Just to wrap it up, where do we started from? We started from the problem of describing cosmic ray propagation in space. Okay, so high energy charged particles in magnetized environment, and we derived first heuristically, then in a more formal way, the conclusion that their motion is a diffusive type of motion, pitch angle scattering. As a consequence, this has a special diffusion type of motion. And once you account for the fact that the scattering centers are moving, these were identified with the alpha n waves, this perturbation in magnetic fields, then you derive a bunch of other terms, among which this diffusion in momentum space, which we call reacceleration, which is conceptually important and important for detailed calculation, but not a major ingredient for the theory of acceleration that was presented by Pasquale Blasi. And then there was this convection term, this adiabatic term, which was instead used in the derivation of the so-called first-order Fermi acceleration, and is very instrumental to it. Then we moved to the treatment of the collisional effects, and we argued that these are important for diagnostic point of view, because we want to access some information about these remote environments where acceleration and transport take place. Okay, one example was shown this morning, how through the X-ray emitted from accelerated particles near a supernova, you can infer something on the microphysics of this supernova remnant in particular. And then we try to, and the other argument that I made was that these energy losses are also important in altering the spectrum of cosmic rays. Okay, so the cosmic rays undergo this transport over tens of millions of years in the galaxy, for instance, and over this time they undergo some collisional interactions. As a result, for instance, the spectrum that we observe at the Earth in the form of cosmic rays is altered. Okay, so today, final step, we want to get back to the transport equation, insert these collisional terms as well, so that we have more or less the full glory transport diffusion loss equation, and provide a few solutions, few toy analytical solutions, which illustrate what's going on. Okay? So far, so good. So I will just argue how to justify the terms that I'm going to add to the equation. Okay, I will start by writing the equation as we wrote without the energy loss terms. So it was for a species alpha, derivative with respect to xi, ij, derivative with respect to xj of n alpha. This is the thank you. This is the spatial transport. This is the diffusion coefficient plus u I dn alpha dxy. This is what we call the advection. Then there was another term, sorry, minus 1/3 du dxy p dn alpha over dp. This is what we used for acceleration. This is the adiabatic term. 1 over p square derivative with respect to p of p square kpp dn alpha over dp. This is what we call second order acceleration piece or diffusion in momentum space. And this is basically what we wrote last time. Of course, this is equal, once you account for the injection and the acceleration at the sources, to some source term. That's the schematic of what we did. And if you remember, this term n is the ensemble average and angular average distribution function. Okay? So far, so good. We derived yesterday and the day before the energy loss rates and the type of interaction rates for a bunch of processes. And if you remember, some of these processes were characterized by relatively continuous loss rates. For instance, I don't know, for the inverse Compton in the Thomson regime, you have some electron upscattering a photon and losing some energy. And if you remember, in this step, there was a very little energy transferred as long as you are in the Thomson regime, namely as long as the energy of the photon in the rest frame of your electron is much smaller than the mass of the electron. Typically, you have something like 4/3 gamma square epsilon, where this is the energy of your photon. And as long as this is much smaller than the electron energy, this is a small fraction of the electron energy, of course. So this is not altering the nature of your particle. You find an electron in a finite space. And in this regime, it will be modeled as a continuous energy loss. Okay? This is applying also to protons in principle in other contexts. For instance, in the ultra energy cosmic ray context, we dealt with this process, proton plus E minus, Bethe-Heitler. Most of the energy is still carried by the proton in the final state. The inelasticity of this process is 10 to the minus 3. So basically, this acts as a continuous energy loss. Okay? So how to describe this type of system? Well, the most obvious example that you have is by a continuity equation, right? You could describe this type of energy carried away like a current of energy. So you know this equation, right? Conservation of mass in a continuum. Well, we just write exactly the same thing for the energy. So if we denote, I don't know, with some curly n of E, which is nothing but proportional to that little n times p square. That's the difference between momentum space and energy space that Pasquale was mentioning. Well, in terms of this, we would have something like dn over dt plus something that goes as derivative with respect to E of E dot, which is a sort of velocity, times n equal to 0, or eventually to some source. This is a gain minus loss. 0 if it's conserved. So that's the way we describe it. Okay. Now the only step is that we have to rewrite this in terms of this differential distribution function in momentum, and you see that it looks something like that. Okay. Remember, n of p is going to be something like n of e over p squared. There is this factor 4 pi p squared that you've seen appearing here and there. So the associated term will be a term that if you put at the left-hand side, 1 plus p squared, derivative with respect to p squared dp over dt, this is in time, loss, let's call it loss for clarity, and alpha. Okay? P square n is the curly n, which enters there, and this is the E dot term. Okay? It's, again, a continuity equation. And here, in this dp over dt, we can include whatever, ionization losses, for instance. Okay? Or for electrons, you might add inverse Compton, synchrotron. Okay? You see that there is always the same n alpha here. So the nature of the particle is not changed. So far, so good. But that's not the whole story, right? Because we learned that there are processes where you change the nature of the particle. For instance, we discussed the idea of, let's use, well, okay, I use this color, but there are processes like, I don't know, carbon-12 hitting a proton, producing some boron 11 plus a proton, something like that. These are spallation processes. So in this case, your species alpha disappears from the equation, and there will be an appearance in the corresponding species beta, which is boron in this case. Okay? So we will write something. Okay. Now, do you know an example, an elementary example of a law where a species is just disappearing from your system? If I have a radioactive nucleus, what happens? You have a law of the type n dot equal minus n over tau, right? You are familiar with that. Okay? So again, you might have some cosmic ray nuclei which are unstable. So you should add a minus 1 over tau times the n at the right-hand side. Okay? There is one difference, is that we are writing stuff in the laboratory frame, our galaxy, and the cosmic rays might be boosted. In general, are highly relativistic, right? So the time here is the time in our frame, which is gamma times the proper time of decay. So apart from that, you may write a term which is like that at the right-hand side. Let me write it like this, gamma. In the case of a radioactive nucleus, this will be 1 over tau, okay? Or 1 over gamma tau in the frame of the lab. If it's not radioactive, still there is a rate of disappearance of this nucleus from the ensemble, which is now collisional. It is related to how often this interacts with your species, okay? So my gamma will be basically n of the target, which basically is the density of hydrogen, mostly for the interstellar medium, times the cross-section, which is implied. In practice, it's all the inelastic cross-section affecting catastrophic losses affecting the nucleus alpha, times, okay, in principle, the velocity, okay, which is close to c. So basically, my gamma entering there is, in fact, a sum over all possible final state of inelastic processes, destroying my nucleus. Yes? Yes. It's n. This is n dot equal minus n over tau. Tau is the lifetime of our nucleus. Is it fine? This is the n over dt equal minus 1 over tau times n. I think that even dimensionally is correct. So in general, if you have a collisional process for making it disappear, it can still be removed from your ensemble via collision with some target. Okay, so symbolically, the gamma there accounts for either radioactive decay, actually radioactive decay, plus all these collisional modes of disappearance. Of course, if this can disappear, it can also happen that an heavier nucleus generates it through the same process. So you have to add another term, which is going to be something like the sum over all possible betas of gamma beta into alpha times n beta. Now, this is symbolic in the sense that in general, this requires a convolution over the spectra, okay? Because this is a differential equation as a function of the momentum of your particle, okay? So in general, if I have a process like that, imagine that my alpha is boron 11, okay? Once the boron 11 is generated in this process, the momentum of the boron 11 is not the same momentum of the carbon. Okay, so this is purely symbolic. In general, this should be an integral with respect to the energy of my primary particle with a differential rate to produce the secondary particle and momentum p. Okay, now for nuclei, that's very close to to be the truth when you rewrite this equation in terms of energy per nucleon instead of momentum. Why? Because I told you that because of the physics of the spallations, the energy per nucleon is roughly preserved in these collisions. This is why if you have a system of nuclei, a coupled system of nuclei, typically you find these equations rewritten not in terms of momentum, but in terms of energy per nucleon. Okay? So that this is simplified. Otherwise, in general, you should think of this term as a sort of convolution. Okay, so in general, this would be something like the integral of some differential rate to produce a nucleus, a secondary nucleus of energy ES from a primary nucleus of energy EP. Then there is your differential distribution of the nucleus with respect to the energy EP, integrated over the EP times the target. Something like that, in general, okay? But basically, that's a good approximation for nuclei produced through spallation. It's not a very good approximation written in that form for antiproton production, for instance. So you have to go to something that looks like this. So far, so good. So basically, we have written a generalization of our diffusion equation accounting for continuous energy losses and also destruction, catastrophic destruction, as well as sort of catastrophic appearance of our species into the system. Plus this term, which is basically what Pasquale has been telling you, modulo the caveat that you have to distinguish still between the accelerated particles and the particles that are injected in interstellar medium. That term is the injection part. In principle, if you have now a model for the injection at the acceleration into the interstellar medium, not into the acceleration process, into the interstellar medium, so what Pasquale called the escape problem, the escape problem from the acceleration side is the injection into the interstellar medium. It's the same thing. Once you have a model for that, you plug it in a source. You have some description of your galaxy in some geometric terms. For example, this slab of magnetized stuff with sources in the plane. You solve for it. You solve, for instance, for the steady state of this guy. And you compare with the cosmic rays at the Earth. And you try to constrain the parameters entering this equation. For instance, the U, the K, et cetera, et cetera, et cetera. That's the rule of the game. Now, there is one caveat, which is related to what Pasquale mentioned the first lecture, namely that we are sitting inside this solar bubble. Okay? So, but for the case of Voyager, we do not access the spectrum of cosmic rays in the interstellar medium. We access the spectrum of cosmic rays near the Earth, where our detectors are. So you should correct for the fact that there is a suppression of the probability that cosmic rays arrive to the Earth due to the solar effect. Now, this is a very complicated 3D problem, but for practical purposes, you can use an approximation which works relatively well unless you go to fine prints of the problem. And basically, this approximation, which is the force field approximation, I just write it here, and there is a reference to the original paper deriving it. But basically, it's equivalent to say that this quantity n, the flux in terms of energy variable, at the top of the atmosphere is written in terms of this spectrum in the interstellar medium, which is the one that comes out of that equation, in this way. This is a model with a single free parameter, which is this potential phi, which is the force field parameter, and whose value is of the order of a fraction of a gigavolt, something like half a gigavolt or so, okay, roughly, times E square minus M square over E plus Z E phi square minus M square. And this parameter is in general time dependent. So practically what it means is that if you have an interstellar spectrum of this sort, what you see at the Earth would be something of this sort, okay? And this is controlled by this parameter here that usually you fit to either directly your data, but you need some benchmark to do that, or this is a time-dependent parameter because it depends on the solar activity. It's roughly periodic over an 11-year cycle of the sun, and it's typically either marginalized over, so you consider it as a nuisance parameter when you fit the data. So you don't know what it is. You just allow for an arbitrary value, and you say, I just look at the cosmic rays in the region which is not influenced by that. Or you fit it to other type of data, for instance, neutron monitors, which are a proxy for the solar activity, or the sunspots, for instance, the number of sunspots versus time. But roughly, this is at the level of 700 megavolt, things like that. So one simple way to neglect about this is that, okay, I focus on cosmic rays above maybe 5 GeV or so, which are little sensitive to this parameter, okay? This is just a caveat to tell you that if you want to compare the result of this equation to what you see on Earth, at low energies, you should be careful because there is this effect to account for. And here, there is no solar effect. This is only related to interstellar medium propagation. This is just a parenthesis. Now, let's consider some solution of that in idealized cases where we neglect some terms and we focus on some terms only so that you get a feeling for what each term does. For instance, let's focus on the case where one is dominated by energy losses. Okay? Let's assume that another comment that I want to make. In all terms of that equation, you see that apart from the factor n, all terms have the dimension of 1 over time. 1 over time, this is gamma is 1 over time, etc. Even this is 1 over time. Okay? This is 1 over time, p cubed, p cubed. Okay? So in general, if you have, for instance, an energy loss phenomenon, and you know whatever, the dE over dt, this E dot here, you can define a characteristic time which is E over dE over dt, tau loss. And similarly, you can define other characteristic times. For instance, advection. There is a U and there is a X here. Okay? So for the typical scales of cosmic rays, the typical scale is the size of your diffusive halo. So U over this diffusive halo would give you a 1 over time scale. Okay? Or if you wish, there is a tau advection minus 1. This gives you a tau advection. So you can, before solving this complicated partial differential equation, you can just compare each coefficient there, and for a given set of parameters, have a feeling of what matters most and what is negligible. Okay? By the same argument, Pasquale argued that typically this reacceleration term is a small correction. So we won't bother about it in the remaining part. So let's assume that you have a system for which the dominating one is this one, this tau loss, which here is this one. To give you an example of where this is the case, that's the case for very high energy electrons and positrons, for instance. Their propagation is dominated by losses, not by spatial diffusion. Okay? So in this limit, we can limit ourselves to solve that only term. Okay? And if we focus on the steady state solution, the only thing that we get is minus 1 over p square d over dp, p square dp over dt loss times n alpha equal to q. Okay? If this is the only term that matters. From this, we derive that n is going to, of p is going to be proportional to minus 1 over p square dp over dt times the integral dp prime qp prime times p prime square up to p. Okay? So now we have seen what's the form of the energy losses for different processes. For instance, this is roughly energy independent for ionization. Okay? This is linear with energy for Bremsstrahlung. And this is quadratic with energy for inverse Compton in the Thomson regime, at least, and for synchrotron. Okay? If you remember, I derived the fact that dE over dt was proportional to gamma square b square, things like that. Okay, gamma is E square over m square. So those two energy losses are quadratic in energy. Okay, so a generic form is to assume that dP over dt is proportional to p to the power L, L being 0, 1, 2 in the cases that I treated yesterday or the day before. And if you plug this in, you will find that n of p is proportional to p minus s plus L plus 1 if s is the injection term spectral index. Okay? So, in general, this spectrum will result L minus 1 times softer than the, or harder if this is negative, than the injected one. Okay? So for the most relevant case where this is a reasonable approximation, which is at high energy for leptons, the energy losses are quadratic. L is equal to 2. This is 1. So you expect that the spectrum is steeper by 1 with respect to the injection one. Okay? It's roughly similar to the injection one if Bremsstrahlung dominates, and it's even harder if you have a system where, for instance, the ionization losses dominate. However, this is less realistic in the sense that in those regimes, this is not a great approximation to forget about spatial diffusion and all the rest. So fine. You can generalize the problem into adding the diffusion, and by a clever trick, you can change your system, your time into a pseudo time. I give you a reference where this is done in the notes. So if you want to see how this is done, you can see. And basically, you go back to the mathematical form of the diffusion equation, purely diffusion equation, but not in real time, rather in this pseudo time. And in terms of this, you can solve mathematically the problem analytically. That's what I mean. You find the green function, okay? Just for your knowledge. Okay, then let's move to a case where instead the spatial diffusion that we cherish so much is important. And let's see some basic solution of this problem. So I told you many, many times that basically, seen from the side, I will consider the galaxy roughly like that, with a gas plane and stellar plane of half thickness little h, and embedded in a magnetized halo, a cylinder of height capital H, capital H up and capital H down. Basically, this problem means that if we neglect the fact that there is maybe a gradient in the source along the galactic plane, maybe there are more sources toward the galactic center and less sources toward the periphery. If we consider this as an homogeneous lab, the only dynamical variable, spatial variable that matters is z, okay? The vertical distance above and below the plane. And this allows us to write this in a 1D form. This is useful because this simplifies a lot the problem, but basically the solution would look like what I'm deriving from 1D also for 2D. The 2D solution can be written as a sort of collections of 1D solutions. You can write in terms, if it's cylindrically symmetric, you can write the solution in terms of a sum of Bessel function, blah, blah, blah. There are some references where this is done, but for simplicity, let me solve the problem in the case of 1D. Okay? In the case of 1D, the equation we care about simplifies, and neglecting, these terms, the continuous energy loss term, which is not that important for nuclei unless you go to very low energies, ionization losses, and without the reacceleration term that we argued, it's not that important, minus derivative with respect to z of k, derivative with respect to z of our n, plus 1 dn over dz, minus 1/3 du over dz, p du over dp, equal q minus n gamma. Then we look for the steady state solution of this equation. And let's neglect for a second this term. Well, actually, I think I would neglect in the following and leave you as an exercise to generalize what I'm saying to the case where u is non-zero. It's more interesting, probably. So if we neglect u, so basically we neglect these two terms. By the way, this is phenomenologically quite a good approximation at high energies. These terms tend to be more relevant at low energies. We have the hypersimplified equation in that configuration. Where I'm additionally considering the slab where sources are located as a delta function. Times delta of z unless this is a radioactive nucleus. Because if this is a radioactive nucleus, I don't need any, sorry, let's write it this way. Yes, I don't need any target, so this gamma is non-vanishing even at z larger than 0, if it's radioactive. Okay, so I cannot use this approximation for a radioactive nucleus. This is, think of the case of carbon fragmenting in the interstellar medium into boron. Okay, this describes the leading terms responsible for the case for the carbon spectrum. Now, let's solve this. First, let's assume that z is different from 0, so we look at larger z, not in the plane. Then there is no source. There is no loss. You just get basically if this diffusion coefficient is independent of z, it's always the same, which is equivalent to say that this diffusion region is homogeneous. Then you get basically second derivative of n with respect to z equals 0. The solution, and this is a function of p and z because I'm looking at the steady state solution, so there is no time dependence, is nothing but some function a of p plus b of p, absolute value of z, because by symmetry I must have the same above and below the plane. And now I can impose the boundary condition. Okay? In the plane, these must be equal to the solution valid locally, which depends only on momentum. At distance z and above, by definition, this must vanish, because this is the definition of my diffusion region, within which I have the cosmic rays. Okay? So I impose that n of p at z equal h plus or minus h is 0. Okay? I impose and I specify these ones. This gives n p of z equal to n0 of p, 1 minus z over h. And 0 if z is larger than h. So far, so good. Now I plug these into my equation, and I look at what happens around my z equals 0. Okay? So what I do is to integrate this equation around a small slab around z equals 0 and apply that form. And what I get is minus 2k. In general, this is a function of the momentum. I assumed homogeneity, but not energy independence. dn dz evaluated in 0, in z equals 0, plus twice h gamma n 0 is equal to twice q0 of p times h. Here I can solve by using this one. Okay, I'm just integrating this one around z equals 0, from 0 minus to 0 plus. Yeah, exactly the same exercise that you did for the show. Huh? And then we found the solution, n0 of p is nothing but q0 of p times a function which I can define tau effective of p, where this tau effective of p, let's write it here, tau effective of p minus 1 is nothing but the sum of the gamma of p plus a term that I denote tau diffusion to the minus 1, where this tau diffusion of p, in general is a function of p, is capital H, little h, over k of p. Okay? So let's see. I will plug in numbers in a second, but let's see what this solution tells us. Okay? The spectrum of cosmic rays in this approximation is the same all over the galaxy in terms of energy dependence. But the magnitude of the flux declines linearly with the height. Okay? This is qualitatively generic for this kind of configuration. Not surprisingly, if you have sources in your plane and the cosmic rays must vanish at infinity at some distance 10 kiloparsec, of course, there are less and less cosmic rays if you move away from the plane. In this simplified case, the spectrum does not depend on where you are, just the normalization. Otherwise, if you complicate a little bit the problem, this might not be true anymore. The other point is that the spectrum is generically different from the spectrum that escapes in the interstellar medium at the source. Okay? Imagine that there is an e to the minus 2, or rather a p to the minus 4, as Pasquale argued in this term. If this term depends upon energy, then what you see at the Earth is not exactly what is injected into the interstellar medium. Okay? And what is this term? This comes from, the inverse of this term comes from the sum of the rate of disappearance of my nucleus from the medium and some time scale which is related to the diffusion. Okay? Now, what did I tell you about the spallation cross-sections? That typically they are energy independent. What about this one? Here there is an energy dependence in this coefficient. So if you do this sum, what happens is that this one, this term here, will always dominate in the final result with respect to this term here at high enough momentum. Okay? So what this is telling you is that imagine that there is a spectrum. In general, this is the qualitative situation that you find in the real life. Imagine that you inject a spectrum like that. What you would see at the Earth is something that maybe looks like that. Okay, flattish and then steeper. Where this is due to the combined effect of the cross-section of the collisional catastrophic loss and the diffusion, and typically this modified power law has to do with the diffusion. So the parametrization of this term here is typically a power law. You saw that already when Pasquale mentioned that this curly f function was going like a power law k to the alpha or whatever he wrote. Okay? So this is typically parameterized in terms of a power law. And in terms of numbers, what you get is that this T diffusion at about few GeV is 10 to the 7 years for age of 3 kiloparsec, little age of 100 parsec, and the typical normalization of the diffusion coefficient, which is 10 to the 28 centimeters square per second. And if you did the exercises, actually in one of the exercises, I provided you the result of a real fit done a few months ago by me and my collaborators in France, okay? And the typical dependence is a power law with an index which is below 1, okay? Pasquale mentioned the Kolmogorov spectrum would correspond to 1/3 in this, and the actual data seem to prefer something closer to 0.5 instead of 0.33, but you get an idea of the typical energy dependence. And just to compare with the gamma, or if you wish, with 1/gamma collisional, this assumes the same value of 10 to the 7 years for a density of the medium ESM of 1 particle per centimeter cube, and for a cross-section of 100 millibar. What does it mean? This is the value, as I said, at a few GeV. Huh? So since this one is becoming shorter and shorter, is this correct? This is the time scale for diffusion. So it's becoming shorter and shorter. Yes, it's correct. So this is declining with energy, with a power law. If you wish, a more complete expression would be something like that times, let's say, 4 gigavolt. I'm inventing the exact numerical value. Huh? But in the notes, you find something more accurate. So this is 4. So if you go to very, very large momenta, these will become much shorter than this one. Huh? So since you sum them, the reverse of these time scales, you can forget about the longer one. Huh? You are familiar with this fact, right? Have you done some resistances in parallel and in series? Huh? And you know that if I sum 1 over R1 plus 1 over R2, this is going to be smaller than the smaller one of the two. Huh? But if one of the two is very large, basically this gives you the other one. And that's what happens here at very large rigidity or momenta. Okay? So we learned that basically we should have a steeper, and then in a second I'm going to tell you how we derive these results about the diffusion coefficient. But we learned that if this is true, the spectrum that we see at the Earth should be steeper than the one that is injected, that is dominated in this steepening by the diffusive effect at high rigidity, and at a low rigidity, there are additional effects. Here we model this through the collisional term. Had I done the exercise of not neglecting this term, this U here, you would find that actually for typical values of U of the order of tens of kilometers per second, it's again the low energy spectrum which is altered and depends upon you. Okay? This is qualitatively a correct lesson. Namely, most of the effects you can think of that complicate the picture that I'm solving kick in at low rigidity. At least that's what we believe. Yes?
So you define gamma, the gamma is the losses, right?
Gamma is the catastrophic loss.
So in the case in which you have no losses, you have to reduce the diffusion, right?
In the case where I have no losses, which means that gamma is not there, gamma is 0.
Right.
So this is 0, and this coincides with this term only. And so this picture would be simplified to something like that.
Why tau d in that case is not capital H square over K? I'm missing a capital H somewhere.
No, I think that the
time is capital H square over K.
Yes, but wait. Okay, first of all, you have always to. No, sorry. I would get H square in this problem if I had sources in the volume H. Yes. I tried. Go ahead. Solve this.
Okay, so you have something like this, and let's write it in a way.
You can start from here. This is correct. Huh?
Right?
Yes.
This is the source term. So I integrate this.
Okay, if you now write Q0 in a different way, yeah, well, yeah, but that's, okay.
So this is Q0. Doesn't matter. This is Q0.
Yes.
So now I integrate this, and I get the usual minus 2k dn z.
Which is
right?
this,
And this
yeah.
one is plus 2k n0 over h. You forgot the name.
No.
Oh.
No, because I defined this as my source term.
Doesn't matter. There is a 1 over h that comes.
Yes, and that's where this h comes from.
No, there is another h because if h goes to 0,
Yes.
okay, there is no dependence. That is
Which h,
irrelevant.
little or
The
big?
small h. It doesn't matter.
Well,
right?
there is
So
0.
The only thing that you know is that you're injecting particles in the disk and they are escaping at
Okay. Yeah, you're right that maybe it's inconsistent. Wait.
So the solution must be Q0
No, you.
times
Okay.
h
Wait.
squared over k. There cannot be small h anywhere.
Okay.
So this
Here.
is fine. Now.
This is fine. I still don't see how you get the from this derivative. You mean?
Yeah, from there.
Okay.
So this is fine. And then there is this. Okay, and this is also equal to this term here.
Yes.
And this term here, this is 0, right?
Okay.
This Q0 of P times H.
Yes.
Right?
And then I solve for n0, and this gives me little h, big H over k times Q0.
No, it's impossible. No, it's impossible. Simply it's impossible. You forgot some term.
I mean, maybe I forgot some terms. What I'm rather sure of, that from the equation I wrote, this one gives the result I wrote. Then maybe this is wrong. But I think it's a matter of definition of what is this term.
So what do you write this term? This term, this is just the dimensionality. I mean,
Yes. Yes.
The diffusion volume is H, so the time
Yes.
must be square of the diffusion
Right,
volume.
but I think it's because you are normalizing your diffusion or your injection to your capital H.
No.
Yes, if I add it here.
This is my Q0. This is my Q0. There is no dependence on H in there.
Pasquale, if I add here capital H, I would get here H squared. Okay?
I'll do it.
Okay, do it in parallel and then find the mistake. I'm pretty sure that from the equation I wrote follows the solution I wrote. Then maybe there is an issue here, but I think this has to do with the way you write this.
There cannot be dependence on small h anyway.
It depends on how you define your source term, I think. But it's a matter.
Anybody film it?
It's online. Well, there is Robocop. He doesn't even work here, it seems. Okay. Okay. So, anyway. So far, so good. Apparently, but. Okay, a couple of things. One is, how do you generalize this treatment if this is not vanishing? Okay, if it's not vanishing, you can repeat the same trick in the case where there is a simple geometry, where again, oh sorry, I erased. With respect to the plane, you have some constant velocity u, up and constant down, opposite direction. Okay, so this is the simplest case, modeling a wind escaping from the sources. This becomes a delta again. This is constant in each part of your slab. So away from z equals 0, this vanishes. And instead of solving this equation, there is a linear equation plus u dn over dz. So what change? You can still integrate this, of course. So what changes is the profile. So this is different. The profile will be different. You plug, again, in this form into the z equals 0 case. You integrate around 0 plus, 0 minus. Instead of getting something like this, which is algebraic, you would get this time a first-order differential equation. Okay? and this you can reduce to quadrature. Okay? So you would get a slightly different shape of the, well, slightly, it depends on how large is U, but you would get a different shape of U, of the power spectrum, if you wish, at low rigidity. Again, there will be some time scale, which I mentioned before, no? This U over H. And you can repeat exactly the same argument, because as long as now U over H is a constant, so it doesn't matter what it is, but at some point it's the diffusive time, the diffusive one which will dominate. So again, qualitatively, you find that at high rigidity, at high momentum, you would get the dominance of diffusion. Okay, this I leave as an exercise. Now, let's go to the most interesting part. What happens if I have a species which is not injected in the medium at supernova, for instance? Okay, already in lecture 1, I think Pasquale showed you this plot with the abundances of different species. And you see that, for instance, in the solar system, but this is true also of the interstellar medium, there are species like lithium, beryllium, boron, which are very rare. Okay? So we assume that this is also true at the acceleration site. So first approximation, for a species like boron, there is no Q term, in the sense of no directly injected stuff from the supernova. However, the Q term exists because of this, in a certain sense. There is some carbon which fragments, spallates, and gives me some boron. Okay? So we can take exactly the same solution as before. What did we find? We found something which is N of 0 P. This is the spectrum seen at the Earth, which is Q0 of P times this effective time of P. But here, for a secondary species, let's say an S, this is not stuff that is accelerated at the source. This is already the propagated carbon species. Okay? So we have to put here something which is nothing but N primary of P0, I should call for consistency, but you know that this refers to our medium, times, 1 over tau, yes, 1 over tau effective, I called it, right? No? Sorry. I don't want to be wrong with notation. So Q0, yes, so no. What is the, this is my Q0, okay? So if to use the same notation, sorry, I should call this gamma of P into S. Okay? So times my tau effective of P. Now we take the ratio of NSP over NP of P, namely, for instance, boron divided by carbon flux. What do we get? Gamma P into S times tau effective of P. This is related to the cross-section. This is basically the cross-section for carbon to fragment into boron times the density of target, the density of the interstellar medium. Both can be determined independently, which means that from this ratio, I get a determination of tau effective. Okay? And what do I find empirically? I find empirically that the ratio of, say, boron over carbon, this behaves something like that as a function of energy. Okay? Now, there is this plateauish feature, and the value here is of the order of, 0.3. So it's not negligible. There is a sizable fraction of boron that comes from, well, with respect to the primary carbon or oxygen flux that comes from this fragmentation, okay? So maybe 20% of the carbon dies during the propagation, okay? And this declines with rigidity. That's the behavior that we find. Now, what did I tell you about the behavior of this function? Well, it's roughly constant at low rigidity because of this interplay of collisional effects and diffusion, and then it follows the diffusion time scale, this low here, at high rigidity. So basically, what you're seeing there is this function. And at large rigidity, you see this behavior. Now, by measuring this, and by knowing the cross-section and interstellar medium, we measure this time scale, which means we measure the effective average diffusion coefficient in the galaxy. Okay? Then you can repeat this exercise for different species, and within errors, at least at a 10%-ish level, you get consistent results. Of course, if each species would, if I repeat this exercise with a different species and I get an inconsistent value of the diffusion coefficient, there is something wrong. One thing that could be wrong, for instance, is that the hypothesis that I've done that everything is homogeneous is wildly violated. If you have enormously many more sources towards the galactic center than you have locally, then this theory is going to break down. Why? Because now each species has a different cross-section and a different propagation time scale. So basically, I get more easily stuff from far away, at low rigidities at least, if this species interacts less. So the volume from which I collect iron nuclei is typically much smaller than the volume from which I collect protons. So in principle, this is one example, why, very simple one, why this simple approximation might break down. There are other approximations that we did, of course.
Pasquale, maybe you want to mention that this is spallation, right?
This is spallation. Right. This. Exactly. Sure. So that, I mean, this is still correct. What is, okay, again, this is not simply written like that. In the case, okay, let's go back to what I told you. To be more exact, this should be the integral over the end, over the momentum of your primary species, the differential rate times my primary species of P prime. This is the comment Pasquale is referring to. And then if I were to do this exercise in terms of the variable energy per nucleon, basically this is equivalent to say that this thing simplifies into a simple Jacobian of the transformation, and that's it. It's quite trivial. But okay, you get the message, I hope. Actually, at high momenta, it's still true that this prefactor would be a known constant. That's the only thing you need to know. I don't have much time, maybe 10 minutes or so. So let me mention something that changes if we relax another approximation that we did. So in all these things, till now, I have assumed that the sources are located in the plane, in this thin region at the center of my diffusive slab. What happens if I don't make this assumption? So how would the equation change? Well, hopefully using the same convention, derivative with respect to z, okay, forget about the other terms which we didn't care about anyway. Derivative with respect to z of n equal only diffusive piece because we don't care anymore. Now I'm using I'm not using anymore the idea that this is concentrated in the slab, but it's a constant term in the whole region, diffusive region, okay? Then this is just something that depends on P and independent of Z. Or if you wish, there is a theta function of, H minus Z, something like that. Huh? So it's the other way around. Theta is defined to be positive when the argument is larger than 0, okay? So it's okay. It's 1 when this is below H. Fine. And then there is, in general, okay, 2H gamma and delta of Z. Okay? Now, not surprisingly, if you solve this exercise exactly the same way we did, you find as a solution N0 of P, it's exactly the same steps. Huh? The only difference is that now this stuff is there even at Z equals 0. Is basically given by tau effective of P times capital H over H of QP. Is this so crazy? Now you have sources which are spanning H, capital H over little h more, and you get such an enhancement in your flux. But that's not the important story here. What I wanted to let you know is that in the previous combination of parameters, you had, for instance, these two, this product. Huh? If I write now explicitly this, let's forget about the spallation, and let's write just the diffusion one. Again, I assume that this is correct. I think it's at least consistent. So what we get would be, this is tau d, okay? This becomes equal to tau d, h squared over k, q. Now, no matter what you do, this is going to be dependent of an additional parameter, an additional combination of parameters, or an additional parameter that the other stuff was not dependent upon. Okay? So imagine that I know this product, or imagine that I know this combination from the boron over carbon. That's what I measure, right? Imagine that I know this combination. Am I able to determine this flux alone by that? No, right? I have a combination of two parameters, and here they enter differently. Now, this example is exactly the proxy of what happens if you want to use, for instance, antiprotons to search for dark matter. Okay? Let's go back to our picture of the galaxy. The logo of the school will be the Alfajores. Standard stuff, stars, supernova, etc., are here. If you attended Fabio's lecture yesterday, you know that the galaxy is embedded in a very big dark matter halo, right? Imagine now that for some reason, dark matter, whatever it is, maybe annihilates into something and eventually produces, say, antiprotons. What's the spatial distribution of this injection term? Is it still in the plane? Of course not. It will reflect the density of the dark matter in the whole stuff. So, of course, the topology, the geometry is not given by the simple exercise I showed you. But it's clear that if you have something that extends even much beyond the thickness of this, and it does, because the typical thickness of this stuff is 3, 5, 10 kiloparsec. The dark matter halo is maybe 100 kiloparsec large, 200 for the R200 radius or so, a lot more. So leading order approximation is basically constant on these time scales. It's not true anymore at the center, but let's assume the bulk of the volume is constant. So basically, you have a term which behaves very differently, and for which the flux at the Earth depends on a different combination of parameters than the one that you have constrained. So if you try to compute the flux that of antiprotons, say, that comes from dark matter annihilation, but you will see maybe this more in detail next week, you face immediately one difficulty, which is that the standard observables we have been mentioning do not constrain all the astrophysical parameters that you need to know in detail the cosmic ray flux coming from antimatter. So not only you don't know what dark matter is, so this is a model-dependent ingredient, but also the type of astrophysics that dark matter signal is dependent upon is different from the type of astrophysical parameters that the standard cosmic rays depend upon. So how do you go around? Well, either you content yourself with very uncertain very uncertain prediction. So roughly, to give you an idea on the current uncertainty on this thickness, it's between 1-2 kiloparsec and maybe 20 kiloparsec. So you see there is an order of magnitude uncertainty into this, just because of astrophysics. Or you try to do something more advanced. For instance, if you start combining this information with other informations, for instance, from radioactive species. Radioactive species, not surprisingly, you have a term at the right-hand side which does not have this delta. So it's the same everywhere in the halo, this term, the decay term. Not surprisingly, these species are sensitive to the thickness of the halo as well, okay, on the top, or if you wish, are sensitive to a different combination of parameters. So at the end of the day, in order to constrain to compute an exotic signal coming from dark matter annihilation or decay is very similar in that respect, you need to do much better than this simple constraint on boron over carbon that we mentioned. Okay? And it turns out that this is a generic lesson for indirect dark matter searches. It's often the case that not only the particle physics of your model is poorly known, but even the type of astrophysical parameters that you need to know in order to constrain that are much more uncertain. So the good aspect, the optimistic way to think about that is that sometimes while thinking about dark matter signature, etc., you end up exploring some new interesting aspects of, in this case, cosmic ray propagation. In other case, maybe gamma ray astrophysics and what else. Okay, so I would stop here because otherwise it would take too long to do other exercise and leave more time for questions maybe. Okay.
No, just to clarify this issue here, it's, of course, it is right that this is formally right, but the Q0 doesn't have any meaning there. So the point is that dimensionally, capital H, small h over k is a time, but it's not nothing. It's not a diffusion time. So the point is that if you want to make a physical statement, it's not just what is h. Capital H, small h over k is only formally a time, but there's no physical meaning. But if you remember what is the injection, this Q0 written in this way, so I mean, it's an injection term, but it doesn't mean anything.
It's normalized in a different way.
So if you divide by a surface, right?
Yes.
Which is whatever, the surface of the disk or whatever, right? So what you get is this say n dot, whatever, no? Per unit time, per unit surface, right? And then you multiply it by capital H over D. This is the solution. Yeah. Right? Yes. At this point, however, neither this nor this has any meaning. It acquires a meaning once I divide this by H and I multiply, and now everything makes sense because this is the rate of injection per unit volume, and this is the
What did I say?
propagation time.
In one case, this is the injection per unit volume in the diffusive zone.
But it's very important, Pasquale, because
yeah,
if
but
you
the
don't
other
account,
is in the gaseous disk.
But if you don't account for this, okay, so what happens when you consider the injection term on the secondaries? The injection term on the secondaries has this ND,
yes,
okay, and then it has this capital H over small h that otherwise you would not have,
yes,
which has a physical meaning again of the average density felt by the
Perfectly
particles in the diffusion volume.
I
So
agree.
what I'm saying is that if you don't do this, everything dimensionally is correct.
no, the
But
solution is
it
correct.
does not
What is not correct is to interpret this
As
as
a
the
diffusion
typical
time.
diffusion time that the cosmic
Okay.
ray goes into the galaxy.
That's my, yes.
Okay? That's the only thing that you
That's
should
my
do.
point.
Of course, the only thing that matters for what I said is basically the ratio between these and these. And that's fine.
But you cannot associate to it any physical meaning. It's just the time.
It's the mathematical
It's
solution
no-
of the problem once you write it this way. Okay? If you want to write in such a way that the effective times that you get are immediately associated to the diffusion time scale, you should adopt the other definition that Pasquale was mentioning. But both are mathematically they are fine. It's just that you shouldn't then attach any
Meaning.
direct meaning to this. Well, there is a meaning. Okay. You know, it's very rare that I prove Pasquale wrong, and let's enjoy this moment.
And they are friends.
We work together, huh?
Magic.
But that's the Italian or Russian way of dealing with science.
It's the more the Russian way. Take into account that Pasquale is leaving for the nice part of Brazil right after lunch. So if you have questions for him, for this Pasquale, better speak now or...
Or shut up to forever, no? Like in weddings. No, you can always write me an email and I will
better to ask
duly
now,
ignore
okay?
it.
Thank you.
Yes.
I don't want to fight. No? I'll try to ask kindly.
Yes.
When you solve the first example for the continuous losses,
Yes.
I understand why you disregard
term.
the first term because you solve the stationary
Yes.
equation, but why this term dominates over the others?
Right. So what I told you is that before even looking at this equation and try to solve it numerically, by the way, there are codes, as long as you do not include any of these nonlinearities Pasquale has been mentioning and I mentioned as well, there are codes that do for you the numerical solution of these, like Galprop, Dragon, or semi-analytical one like Cuisine, etc. But before solving this, you should always have an idea for the problem that you are looking at about the scales of each of these terms, the sizes, the relative sizes of each of these terms. That's how I started. Okay? Now, if you look at the typical loss time, which I defined as minus E over d over dt, for electrons, say, of 100 GeV, you realize that the time scale associated with this term is much shorter than all the other time scales of the other terms. Okay? If this is true, and if this exercise teaches us anything general, qualitatively, what you would find is always that you will have an effective time modifying your source term, which is the sum of the inverses of the respective times, right? So if I know that one is much, much shorter than all the others, I can do many complicated things, but I will end up with something that resembles this. And so at the end, the only effect that matters will be this one. Okay? So in general, what will happen is that in the case I was mentioning, where you can, for instance, this one plus this one, you can solve again analytically. What would happen is that you have this pseudo time, this auxiliary variable, which is a sort of in between the time and an energy loss variable.
Okay.
If
like
this
the
is
equivalent.
dominating with respect to the other, basically you are solving directly your problem in terms of energy space, and that's what gives you the result. Of course, this would have taken 2 hours, and you would have looked at me like, what did you do? But that's the trick that you do in order to solve in a more complicated way. Now, why I did that? Because I know the solution. I know that electrons behave this way. If you don't know that, you should take the formula for the energy losses, compute these characteristic timescales, compare with these timescales that I showed you here, and you will see that if you go to hundreds of GeV and TeV, those ones will become much shorter than those ones. Okay?
Okay, so that time you mentioned is like to find that equivalent resistance of the example. Okay, thank you.
Okay.
So on the first example, you mentioned where the tau loss dominates. I missed the part where you said what regime that specific example was valid.
Repeat the first part of the question.
It was when you solve the equation only considering the
energy losses.
Yeah,
Or
no,
no?
only considering that term over there, the yellow term.
Yes, these
Yeah,
are
yeah,
these are
energy loss.
continuous
Exactly.
energy
Yeah,
losses.
yeah.
Continuous energy losses. So yes.
So my question is, in what regime is that valid? I think you mentioned it quickly, but I missed it.
It's the regime where the dominant transport effect is due to energy losses. So empirically, I can tell you that this is quite close to truth for very high energy leptons. Okay, TeV electrons, for instance. These are basically described by this type of equation. Of course, there is also another way to deal about that. Imagine that I have a system which I do not resolve spatially, so that I integrate over spatial coordinates. This is often the case that you find in modeling very remote accelerators, right? You have a blob, you say this is homogeneous, blah, 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 etc. Then basically you integrate over space, and the only variable you care about is energy. Then you don't care very much about things like, I don't know, an energy-independent diffusion coefficient or things like that. So this is another case where basically the only things that matters are energy losses. Okay? So sometimes you may model a blob where you assume that basically it's diffusing in an energy-independent way, and you do not resolve the morphology of this blob just by a continuity equation in energy space, and that's it. This is another application that is...
So in other terms, if we had put that h when p over p dot is much smaller than h squared over d, but without that h,
no,
you
that's
cannot
not
see
true.
that.
Whatever you do, no, that's not true. Whatever you do, as long as you normalize each term consistently, you can always compare them consistently. So you don't care about the absolute value of each time scales, only the relative ones. What I said is correct. Of course, the day you say how long it takes for a cosmic ray to be advected in the galaxy, that's a different story. You should be careful to what he said, okay? But if you just want to compare the terms, just be consistent, that's fine.
Can we have a question that drifts away from this? Because I have to go for lunch with the two of them. So please, a question far away from this problem, okay?
I don't know if you mentioned it, but for example, the losses for hadrons,
yes.
photomeson production,
right.
is considered as a continuum losses or as a catastrophic loss?
Very, very good, very good question. So basically, there are even codes where this is not even treated. Okay, so one trick to treat it is to add exactly this same shape, this same form. Okay, you take the integrated one, so to speak, or the differential one, and you add this, which would be like the n alpha of p, and then here you have the cross section for loss via photopion production at a momentum p, blah blah blah. So the loss is not that much of a problem, and then you reinject here the proton with a degraded energy associated to that. This is the way usually this is treated. And in those contexts, they are called, for some reason, tertiaries. Typically, they are called tertiary protons, and this comes from antiprotons, in fact. Because this term you are mentioning is extremely important for antiprotons calculation. Extremely important. At low energies, it's important for antiproton calculations. So what happens if I want to produce an antiproton? I have, imagine that I have proton-proton production of an antiproton. Then there will be energy losses of this antiproton. I may even have antiproton annihilation. Associated to this term of energy losses of antiprotons, I might still have an antiproton in the final state. Since the antiprotons coming from proton-proton are called secondary antiprotons because they are not present in the source, this term is called tertiary antiproton channel, but it's nothing but the result of the energy losses or inelastic processes, to be more generic, affecting these particles. So for protons, coming back to your question, for protons or for nuclei in principle, for nuclei it doesn't really matter for the simple reason that these spallation cross-section are way more important than the pion losses, okay? Just by comparison, the typical cross-section of hadronic spallation interaction are 100 millibarn or tens of millibarn or things like that. The other one, if you remember what I told you yesterday, is below the millibarn. Is maybe 700 millibarn or things like that. So you neglect them, it's not a big deal. For protons, that's going to be the dominant energy loss channel. Of course, there is also energy source from spallation on heavier nuclei. So the protons are sourced by the supernova, are sourced by the fact that you can destroy an helium nucleus, for instance, and this will give you protons. But there is also another term, which is the energy loss of protons onto other protons producing pions and protons or neutrons or other hadronic garbage. And then as a result of that, you degrade your energy. And the way you treat it is in this way. So you have to go back to this distribution notation where you have the differential cross-section. But in some codes, this is not even included. It's not a huge effect, but it can be, percentage. And now the data of AMSO2 at low rigidities for protons are at the same level. So if you want precise prediction, in principle, you should account for this term.
So in that equation, we have a injection term that is provided by source, right?
This one, yeah.
Yeah. So what would I do to obtain a term for acceleration process?
So that's exactly the topic of Pasquale's lecture. So you see that he wrote it something like that. So this would be, let me be clear on this. This would be the cosmic ray flux, so the number of cosmic ray particles with this energy spectrum per unit time injected on average by supernova in this volume that he mentioned. This is the surface of the galaxy, for instance, if this RD is the galaxy. So imagine that you have one supernova, or whatever, 3 supernova per century. So the Q term would be something like 3 times century, roughly, times whatever spectrum a supernova gives you, each supernova, times divided by well, depends on now on your normalization, divided by this is, here it's a surface term, so this is the area of the disk of the galaxy. Okay, this is what this term looks like. Okay.
Okay, so but is there a way to account for acceleration in the term of the continued energy losses with the with a rate of acceleration?
Which one? This one?
Yes.
This
No,
one
no,
or
no.
this one?
That one. The yellow one.
Okay, normally here you plug in the energy losses. The only term for, okay, it's not completely exact, but in this, okay, I should say you something important. This whole factorization that we have been using, so we splitted somehow the material between source, acceleration, and propagation. Of course, there is no guarantee a priori, if you know nothing about astrophysics, that this is true. You might conceive models where the acceleration and the propagation are basically simultaneous processes, not happening on wildly different time scales. For instance, the second-order Fermi acceleration was such an idea. Okay? The cosmic rays are accelerated from the pool in the interstellar medium. You might have even shocks traveling around in your interstellar medium unassociated to visible supernovae, for instance. But in practice, the empirical evidence suggests us that instead you have a good approximation, a factorization between the acceleration, which happens on the typical, 10,000 years or a few tens of thousand years at these sites, and the propagation, which happens on these tens of millions of years time scales. These are factorized. You have to take into account now the energy losses in the interstellar medium, because over tens of millions of years, they are not necessarily negligible, okay? While they are, to large extent, over the 10,000 years that Pasquale was mentioning for a typical evolutionary time scale of your supernova remnant. So this is the whole logic of this factorization. Of course, this is an idealization. Nature does not know about that, right? So if you want, I can ignore this term, and I could put, what is these shocks that he's talking about? It's associated to this term here, right? So I could imagine that I model my velocity field in the medium as something which is quite trivial, plus from time to time I have this thing, which is where the acceleration takes place, and then I wouldn't have this additional term here. It's this inhomogeneous part of this term which gives me the acceleration. Okay, so the term, there is no, okay, again, there are terms that are not described within the approximation of the transport equation that I've done. In particular, these are the right-hand side term that he was mentioning, accounting for the dissipation and all that. But apart from that, the phenomena that he has been using at the shock acceleration or the phenomena that he's been using at the second-order Fermi acceleration are already in. They are already here and here. It's just that for the sake of the argument, we treat the part which is concerning the bulk of the volume of the galaxy separately from the part which is concerning the size, the discrete size of acceleration. You might ask me even another question, which is why you are considering the acceleration size as spread out continuously in the volume of the galaxy. We see that these supernovae are not exploding, are not injecting regularly, that many cosmic rays per unit time like a jelly in the galaxy. These are very clear, discrete objects that explode, last for a few tens of thousand years, and then maybe over 10 to the 5 years, they are gone, right? So, in fact, you might wonder, is this a good approximation? Is the assumption that this term is continuous in space-time a good approximation? You can do this calculation with Monte Carlos, even semi-analytically, and you realize that typically, for most observables, this leads to errors which are smaller than past experiments, but now for AMS. For AMS, the typical stochasticity is not negligible anymore in some energy range with respect to the error bars of your experiment. So in principle, you should be careful not to rule out some transport model because of the approximation that you did in the injection model or the escape with respect to supernova. So all these problems are quite new in some sense. Huh?
More questions? Well, then it's my pleasure to thank both of the Pasquales again, together with you. And offer to both of them, before they take off, a small sign, token of our big gratitude. Pasquale, if you come with the other Pasquale too.
Does it explode?
Pasquale, it explodes when you're far away from me. Okay? Thank you very much,
Would
guys.
you arrest me in the airport?
We have been mugged.
You have been mugged.
Ah,
I
it's
think.
a
You
mug.
have definitely been mugged.
Very good. Thank you. Thank you.
And you can actually purchase yours. I'm not going to tell you the price because it looks very bad, but you can get one yours. Thank you very much again. You are going to be staying for the afternoon if we're going to be having a discussion session. Pasquale, you can leave it.
I can leave
Yeah,
it?
you can
Okay.
leave it. That's fine. The students will think about
I
it.
got this privilege.
Thank you very much again for the classes, both of you, and thanks for coming. So we reconvene at 3 p.m. sharp, okay? Sign for the dinner, if you're planning to come for dinner right now or before. And don't forget the gift from Pasquale Serpico.
Sì, credo sì.
Come cazzo fai a interpretare fisicamente quella cosa?
Pasquale.